We've talked quite a bit about Java parallel streams. You've seen quite a number of examples. You've got a chance to play around with it in the assignments you're doing for the course. Let's kind of take a step back and talk about when you should use parallel streams. First thing to note, parallelism is not a panacea. A parallel program always does more work than a non-parallel program. It needs to partition the overall task up into subtasks. It needs to process all these subtasks, which of course is usually all that a sequential program has to do. And it needs to combine all the results back together again, which is something that a sequential program doesn't have to do. So a sequential program doesn't need to do tasks 1 and 3. Both parallel and sequential programs need to do 2. So again, sort of maybe stating the obvious, as we've talked about a number of times now, if the time needed to partition the overall task into subtasks and the time needed to combine the subtasks back together again is more expensive than running the subtasks in parallel provides a win, then you're going to end up with a sequential program doing better. As a consequence of this and some other factors we'll talk about, a parallel stream should only be used under certain conditions. And you have to understand what those conditions are. And there's a nice kind of summary of this here at this link from my good friend and colleague Doug Lee, talking about when to use parallel streams. This was actually written by the people who wrote the parallel streams framework, trying to give you some guidance on that. And there's other sources of guidance as well we'll talk about. So parallel streams are most useful under certain conditions. For example, when behaviors, those are the things that are functional interfaces and method references, lambda expressions, and so on, when behaviors have certain characteristics, they're a win. Are the tasks that are running independent of each other, or what we like to call embarrassingly parallel, where there's no dependencies or no need for communication between tasks in order to carry out the processing. And of course, the example I always like to use is laundry. So you can run your wash in parallel. You can do your drying in parallel. They don't depend on them. Obviously, you have to do well, not obviously, but most of the time you do your wash before you dry it. But once you are done with washing, you can do drying in parallel. And there's lots of examples. I have a bunch of examples in my GitHub repository of searching for things like phrases in the works of Shakespeare in parallel. And this example, search with parallel streams, searches each phrase in parallel. You can search each input string in parallel. You can search chunks of each input string in parallel. And you can do them all at the same time. And next class, we'll talk about how to do all those things in parallel. It's a really cool example. Another thing that makes a parallel stream a win is if the tasks being performed in parallel, the subtasks, are computationally expensive, which is just a fancy way of saying if the behaviors that are part of your stream take a long time to run for each of the elements that you're processing, a parallel stream is most likely going to give you a benefit. And another way to look at this is if you have lots of elements to process. This is the N we keep talking about. So if you have lots of things you need to process, this is the famous terracotta warriors in China, and you want to do something with all these things, you got a large N, then obviously parallelism is going to help. If you want to have, if you want to go and clean the terracotta warriors to get dust and cobwebs off of them, having an army of workers to do this is going to go a lot faster than having one person go one warrior at a time, which will take forever. Something else that helps is if the sources can be split evenly and efficiently. The more you can do that, the better. If you recall our discussions about linked lists versus array lists and so on, the ones that can be split evenly and efficiently are more optimized for parallel streams. So these two elements, computationally expensive, applied to many elements of data sources when coupled with independent, leads to the so-called NQ model, where N is the number of data elements to process per thread or per core, and Q is a quantification of how CPU intensive the processing on each element is. If N and Q are big, that's the right place to be. If N and Q are low, then you're not going to get much of a win. So here we go. We're searching for phrases that match in the works of Shakespeare. That parallelizes very nicely because there's lots of processing to be done to search for each phrase. There's lots of phrases for our use case. There's lots of works of Shakespeare. So there's lots of stuff, and so it speeds up very nicely. Something else that's maybe sort of obvious, but I'll just state it because there's no sense in not stating the obvious, if there are multiple cores. If you have one core, maybe you'll get benefit from parallelism under the right conditions, but you're better off having cores. And of course, the good news is modern chips have lots of cores. So under the right conditions, Java parallel streams can scale up nicely on multi-core and many-core processors. And you can see here that for some configurations, we get a much bigger bang for our buck by using very aggressive parallelism models than we do from using sequential models or from using more conventional parallelism models. And we'll talk about this parallel split iterator case study later. So that's the end of the discussion of when to use parallel streams. Now, not surprisingly, there's also another discussion we're about to have, which is when not to use parallel streams.